In this section we're going to look at dielectrics and we're going to look at susceptibility, permittivity and the dielectric constant. So what we know is that the polarization will usually result from an electric field, and in most dielectrics the polarization is proportional to the electric field and it will point in the same direction. Now that is, the electric field will line up the atomic and the molecular dipoles. In linear and isotropic dielectrics, which accounts for many substances, the polarization is proportional to the electric field, and that is for when the electric field is not too strong, and it will be given by our polarization will be equal to chi times epsilon naught times the electric field. Chi here is the electric susceptibility for a particular material. And this will depend on the microscopic structure of that particular substance. The dielectric is homogeneous if the electric susceptibility is independent of the coordinates. Now the electric field is the total electric field. That is, it accounts for both free charges and it also accounts for polarization. Now in linear and isotropic dielectrics, the electric displacement can be written as, and we found this previously, the electric displacement will be equal to epsilon naught times the electric field plus the polarization. And now we can write this out as epsilon naught by 1 plus chi times the electric field, which would be equal to epsilon naught times epsilon r, where epsilon r now is the relative permittivity, times the electric field, which is equal to epsilon times the electric field. Epsilon is the permittivity. Okay, so in here what we've written is our relative permittivity is given by 1 plus chi e, which is equal to epsilon divided by epsilon naught. Okay, and the relative permittivity is dimensionless. Okay, so that is, it has got the same units as epsilon naught, which is farads per meter. Okay, so the unit of epsilon naught is farads per meter. The quantity epsilon is a permittivity. So now for linear and isotropic dielectrics, we can write out an expression for the polarization, and our polarization, as given above, is equal to epsilon naught times chi v times the electric field. And now we can write this out in terms of the relative permittivity, which is given by epsilon naught, epsilon r minus 1, times the electric field. I should also mention that the relative permittivity, of course, is also called the dielectric constant of the material.